It doesn't, there we go. All right. Welcome everybody to the day 3 of the PM3 2021 user workshops. Clara and I are going to be, and we're really looking forward to hearing from all the presentations. The order of this morning will be Laurence Lu and then Clara Sun, and then in the afternoon, Dr. Daniel Goldman and Dr. Karche after the lunch break. There will also be presentations by Chang Jin and Sarah Parveen uploaded to the YouTube channel after the workshop is completed. Just as a friendly reminder, we're recording all of these sessions, so you can keep your cameras on or off, depending on what you're comfortable with. And yeah, without further ado, let's begin with Laurence Lu, who's presenting about 1D cerebral structural modeling.
All right, I'll share my screen right now. Can everyone see this?
Yes, we can.
All right, so I'll start. Hello, everyone. My name is Laurence Lu, and I am a second-year undergraduate student in the medical science program at Western University. And I first would like to thank Dr. Karche for giving me this opportunity today and also hosting this workshop. So today, as part of the 2021 PM3 workshop, I'll be talking about 1D cerebral structural modeling, and specifically solid modeling of the aorta brain complex. The aim is to prepare the family of BRAVA human arterial blood flow models for dynamic CFD simulations and construct hemodynamically active brain aorta models to better understand cerebrovascular disorders, such as stroke, vasospasms, aneurysms, and also evaluating the effectiveness of current treatments. My email is written on the slide, so feel free to contact me if you have any comments or questions. So to start off, 87% of stroke patients experience ischemic stroke, where there is a blockage in an artery that supplies blood to the brain, reducing the blood flow and oxygen, and it will damage the brain. We can construct and use hemodynamically active brain aorta models to test variables such as flow rate, pressure, Reynolds number, and wall shear stress to improve treatment and detect early warning signs for these disorders. So for this presentation, I'll first go over the brain model data repository, talking about the data that will be used to create the idealized brain and aorta. I'll then go over how we use VTK visualization to create a 3D representative model of the brain arterial vasculature and how that will be used to gather statistics about the radius and the length components that make up the brain model. Next, I'll talk about the creation of an idealized aorta and how we will use that model alongside the brain arterial vasculature to then complete the aorta brain structure complex, which is a solid model. So to begin making a brain arterial model, we first had to obtain the brain connectivity structures from the publicly available BRAVA dataset from Susan Wright and al. This database was able to provide and visualize digital arterial reconstructions from 61 MRA magnetic resonance angiography image subjects. The results of the digital reconstructions of the brain structures were saved as ASCII files in the SWC format. This data was able to arrange the characteristics of the branching brain structures in a table of 6 columns labeled node number attribute, the X coordinate, Y coordinate, Z coordinate, radius, and parent of node, where the lengths are in millimeters and the columns are separated by a tab. This data will be useful in finding coordinates of carotid inlets and potentially finding bifurcation points, where a parent node branches off to 2 distinct nodes. Another important step in connecting the brain model to the aorta model was to identify inlet nodes where the 2 models will connect. This can be found using the brain model and finding the nodes with the lowest Y coordinate. So first, to create representative brain structures, we can use the SWC files gathered from the BRAVA database. We can convert them into VTK files and put them into ParaView to visualize the models. As you can see on the left side, figure 8 and figure C, they show 2 of the 61 total brain vasculatures made. These images show the backside view of the brain vasculature with the left carotid on the left, the basilar in the middle, and the right carotid on the right. The end inlet nodes of these three arteries will be connected to the aorta model shown later in the presentation. Thus, it was important to find all the inlet nodes for all 61 brain vasculatures, so we can manipulate the aorta models accordingly and connect the two parts seamlessly. So like what my colleague Gabrielle has done, I was able to use MATLAB and the Brava SWC files to gather network statistics for each of the 61 brain models. Specifically, we were able to find the radius and length distributions of the brain. So for figure B, we have an example of the radius distribution histogram, where the x-axis shows the radius in millimeters and the y-axis shows the number of nodes with each radius. In figure 2, we have a length distribution histogram, where the x-axis shows the length between each node in millimeters and the y-axis shows the count of the lengths. Next, to create an idealized aorta models, we were able to find the lengths and radius of each artery that composes the entire aorta from an article written by A. Mellis et al. In the Journal of Biomechanics. For example, by getting the lengths and radius of the left, right carotid, and the vertebral arteries, and also the ascending aorta, we can form a shape of the aorta model. Like the brain model, we can use an SWC file with nodes and coordinates to create the aorta model, and then turn the SWC file into a VTK to visualize the aorta. With this idealized aorta model, during simulations, we can use the ascending aorta as a central point of blood flow and pump blood from one location where it then separates to different arteries, such as the carotids and the vertebral arteries, to join the brain and vertebral arteries. This model is also flexible, so we can move the left, right carotid, and the vertebral arteries to join the brain inlet coordinates, which was found in the SWCs. By using a 1D solver such as PM3 SimVascular software, we can also do CFD simulations on these aorta models and analyze variables such as area, pressure, Reynolds number, and wall shear stress. On the left side, we have an aorta model showing changes to the flow rate. We can see that the left inlet node of the aorta has a higher flow rate, while the outlet on the right shows less flow rate, and it's approximately 100 times less. It is also important to note that the larger the artery, the larger the blood flow. On the right, we have an aorta model simulation showing animation created by Clara Sun, showing the wall shear stress throughout parts of the aorta when blood is being pumped. As we go through the simulation, I'll show the simulation right now. We can see that the vertebral arteries go from being a dark blue to a dark red, indicating that there's a 100 times more wall shear stress over that time. It is also important to notice the wall shear stress also becomes 100 times more only in the vertebral arteries compared to the left and right carotids. On this slide, the image shows a complete aorta brain structure complex, a solid model, where at the bottom you can see the SWC of an aorta model, and the top is the SWC of a brain vasculature. There are three connections that join the aorta with the brain. We can use the inlet data from the SWC to find the coordinates where the brain meets the aorta model. From this image, the right carotid connects to the right brain inlet, the left carotid connects to the left brain inlet, and the two vertebral arteries all join and connect to the basilar, the middle inlet. As you can see, the three inlets leading the brain are joined to one central artery, the ascending aorta. And once again, this allows for simulations to have one source of blood flow and ensure that all three inlets receive constant flow leading up to the brain. So with this aorta brain complex, like the idealized aorta model, we can test it on Beluga and look for variables such as flow rate, pressure, wall shear stress, and get a better understanding on cerebral vascular disorders and assess the effectiveness of current treatments. In this image, it is demonstrating the wall shear stress through various parts of the aorta brain complex. So overall, we were able to construct a hemodynamically active solid model of the aorta brain complex. And using this model, we can better study strokes and it is also capable of the study of blood flow reserve, vasospasms, aneurysms in humans, and possibly can be used for animals such as rats. In the future, I would like to use this model to quantify the effectiveness of treatments currently used, such as thrombolysis, mechanical thrombectomy, cerebral blood flow reserve, risk of aneurysm rupture, as well as pharmacological treatments such as TPA, and find ways to improve these treatments and find new ways to detect early warning signs for aging-related diseases and analyze fluid flow in arterial geometries. So now I'm done with my presentations, and if you have any questions, feel free to ask.
That was a great presentation, Lawrence. Thanks. So if anybody has any questions, they can either type them in the chat and I'll read them out, or they can just unmute their mic and ask.
I'll start off, Tim, if you don't mind.
All right.
So Laurence, thank you for so elegantly organizing your work in these short few months. I'm really thankful for that. Could you sort of comment on, you said that you will do some future work here. You've made a list of at least 4 studies that you say you're going to be participating in. So do you have some idea on how these studies will proceed, starting from now? Now that you've come to this stage, how will it proceed from here?
I think first we need to make sure that the models are good and well done and good to go. And then next, I would like to find ways we can incorporate these types of disorders and see if our models would work and see if that will help and do it step by step, going through each process.
So the next immediate step that you foresee is assessing model sensibility.
That's right.
Okay.
Our current models.
Thank you. Thanks, Tim.
Quick question, Lawrence.
Oh, yep. Yes.
Hey, very nice talk. Near the beginning, you showed a couple vessels with very high wall shear stress. Could you tell me what that was?
I'll show my PowerPoint right now. Is it this one?
Yeah.
What was the question again? Sorry.
So why did the shear stress get so high in 2 of those vessels?
This was just showing, this was just 14 frames of the blood pumping. So it wasn't the whole process, but it showed significant changes in the wall shear stress.
So it's showing time-dependent phenomena, is that what
Yeah,
you're
that's
saying?
yeah. So it's the first 14 frames of this simulation, and it's when blood is being pumped from the aorta. And we noticed that the vertebral arteries received stronger wall shear stress, probably due to like a radius issue or something along those lines.
Okay, all right, thanks.
Just to add to what explanation Lawrence has provided, Prof, I believe we have to more closely look at the boundary conditions. As of now, the boundary conditions are applied to the point where the model does not fail numerically.
Okay. Well, I understand that. Yeah. So it could be partially working out the ideal boundary conditions.
That's right. As we discussed yesterday, the boundary condition that comes out of our reduced order human circulation model has a positive aortic inlet. But the convention used by SimVascular for the 1D models and the 3D models is that the aortic inlet flow should be negative, as pointed out by Mia Wang.
Okay.
So that is just convention. It is the way you take your normal to the surface, something like that.
Yeah, if it's a little bit confusing with SimVascular, because I think with the 0D modeling, they actually flip the convention. So you have to be really careful with choosing your inlet boundary conditions. If there's no more questions, then I think we can move on to our next talk, which is Clara Sun. She's going to be giving a talk titled Data-Driven Rat